Okay, the next video in this unit is going to be how to solve equations that are in the form of exponential equations. So what that means is that we're going to be looking at equations that have x's up in the powers of their equations. So we're going to start off with some simple examples that don't require logarithms in order to solve. And then we're going to look at some more complicated examples that are going to require logarithms to solve. So this one, this lesson goes hand in hand with what I've been telling you in class, that if you don't have a scientific calculator or a calculator that does logs at all, it's going to be very difficult to do these problems. Now, the problems that you see on this first page are actually problems we can solve without the use of a calculator. So I'm going to show you how. So there's a property that says if you have two exponentials set equal to each other and their bases are the same, all you have to do is set the powers equal and solve for x. So in this first problem, notice that both of the bases here are 3's, and I've got these two powers, 4x plus 4 and 12. In order to solve the equation, all I have to do is take the powers down, set them equal to each other, and solve for x. It's really supposed to be that easy. So to solve this, I would subtract 4, you get 2x equals 8, and then if you divide by 2, you get x equals 4. The next problem, notice that the two base numbers are not the same. However, if you recognize these, they're both powers of 3. So just like we did in the original logarithms section, where we were able to change the base numbers into what we wanted them to be, you can do that in this problem too. So rather than leaving these 9 and 27, I'm going to take that 9 and I'm going to take that 27 and I'm going to write them in their power of 3 form. So I'm going to rewrite 9 as 3 squared. I'm going to rewrite 27 as 3 cubed. And then the rest of the power that's there remains the exact same as what it was before. So this had a 2x before, so it's still going to have a 2x up there. This had an x minus 1 before, so it's still going to have an x minus 1, just like it did before. So the rest of the problem doesn't change. The only thing that I've changed is the 9 and the 27 are now written in base 3. Now, why do we do that? Because just like the last problem, I can take the two powers and I can just set them equal to each other. So on the left side, 2 and 2x give you 4x. And on the right side, distributed, 3 times x minus 1 gives you 3x minus 3. So the equation now is just a simple linear equation to solve. All I'm going to do is subtract 3x from both sides, and you get x equals negative 3. The problem is done. The next problem, again, notice that my base numbers aren't the same, but I can change them both. I can change 4 and 1/2 to both be powers of 2. So if I rewrite 4 as power of 2, that's 2 squared. If I rewrite 1/2 as a power of 2, that's 2 to the negative first power. Now again, the rest of the problem doesn't change. This had an x up there, so it still does. This had an x minus 3 up there, so it still does. Once I have the two base numbers as the same, now I take the powers down and I set them equal to each other. 2x equals negative x plus 3, distributing that negative 1. Next step would be to add x to both sides, so 3x equals 3. And if I divide both sides by 3, we get x equals 1. So the last two problems down here are similar fashion, so I'm going to do the setup for them, but we're not actually going to follow through and solve because they're solved just like these last ones. So the first thing I would notice about these is 100 and 1000 are both powers of 10. 100 being 10 squared, 1000 being 10 cubed. The rest of the problem doesn't change. The 7x plus 1 still comes down and is up there. The 3x minus 2 doesn't change. It still comes down and is up there. So at this point, we would set those two powers equal. And to finish the problem, you'd solve for x. Last one, 81 and 1/3 are both powers of 3. We would write 81 as 3 to the 4th power. 1/3 is 3 to the negative 1st. If we bring down the remaining portions of their powers, we've got a 3 minus x in the first exponent, and we've got a 5x minus 6 in the second exponent. Again, since the base numbers are the same, we can take the powers down and set them equal to each other. So 4 times 3 minus x would equal negative 1 times 5x minus 6. And then you would solve that linear equation to figure out your value of x. Now again, all 5 of these examples are problems where logarithms aren't necessary in order to solve, because I was able to take both sides of the equal sign and make them the same base number. Now, is that always going to be the case? Unfortunately, it's not. So in the next page, we get into problems where we can't do what I just said. And if you notice and look at the problems, they look a lot more complicated. So looking at this first one, there's no way for me to make 4 and 11 the exact same power base. It's impossible without using a calculator. So what we're going to do is we're going to solve these problems using a logarithm. Now here's the deal. There are 2 different mindsets or methods that I could show you on how to do this. One of those is that we can use the fact that we know exponentials and logarithms are inverses of each other. So what do I mean by that? I mean that if I took this problem, 4 to the x equals 11, what I could do to both sides of the equal sign is I could use the inverse operation in order to get this x out of the power. So what do I mean by that? I mean that I can, if I want to, take the log of both sides of this equal sign. So when I take my log, the way we get logs and exponentials to cancel out is by taking the same log base of the exponent base. So we're taking the log of both sides. Now, if I do that to the left-hand side, I would have to do that to the right-hand side. So I would be taking the log base 4 of both sides of the equal sign. Now, what does that do for me? The log base 4 and the exponent base 4 now, they cancel each other out. And all I'm left with is what x equals. Now, the right-hand side, you can't really do anything with this, log base 4 of 11, because it doesn't simplify into a nice, neat number. Now, what if I want to put it in a nice, neat number? Some of you might be lucky and have a calculator that lets you input whatever log base you want. Most of you, I'm going to assume, probably don't have a calculator that lets you do that. So what if I wanted you to give me a decimal answer for this? How would you do it using a calculator that doesn't let you type in whatever log base you want? That's where change of base formula comes into play. Remember, change of base formula is a way to take something like this and evaluate it inside of a calculator that doesn't let you put whatever base you want. So whether you have a graphing calculator or you have a scientific like this one, it doesn't really matter. All I'm going to do is change this using change of base formula, and there's 2 ways to change it. You can change this into log of 11 over log of 4, or you can change it into the natural log of 11 over the natural log of 4. And if you remember from change of base formula, that's just log of the big number over log of the small number. Both of these are going to give you the exact same answer. So regardless, if you have a calculator that lets you type this in, great. It's going to give you the exact same answer as typing this in, which will give you the exact same answer as typing this in. So using this calculator, since I'm not able to type in whatever I want out of this, what we're going to do is we're going to use the change of base formula. So I'm going to use log this time. Now my log button on this particular calculator is right here. So all I'm going to do is press log 11. Oops, that's log 1. Log 11, and I'm going to divide by log of 4. And when I press enter, I get a decimal. And I'm going to round this to 4 decimal places, so 1.7297. That is the same answer as if I would have done natural log. And so to prove that, I'm going to do natural log of 11, divide by natural log of 4, and we should get the same answer. And if you look at the answer, we do. Okay? So that's one way to attack a problem like this. Use an inverse operation and take the log of both sides. The other way to look at this would be to just simply switch the form of the equation. which some of you might like doing. I'm going to imagine most of you probably won't do this, but you can do it this way if you'd like. Number 1, remember changing the form. Use the pattern. Circle the number and go around the circle. So if I wrote this in log form, I would use log base 4 of the other number 11, and that equals the power up top. Now if you look at what I just wrote, it's the exact same thing as what I have here. So whether you log both sides or you just simply change the form, you actually get the exact same result. Figuring out the decimal for this is going to be done the exact same way we just did with change of base formula. So it's just two different methods in order to do the same thing, two different thought processes. I'm going to venture a guess most of you will probably do using the inverse by just logging both sides. Now let's talk about one other way to do this. So you'll find that a lot of teachers just tell you to log both sides. They're not going to tell you to use a specific log base. They're just going to say log both sides. So what do you think they mean by log both sides? They mean take log base 10, and just do this. Log 4 to the x equals log 11. Now, why would I want to do that, and what does that do for you? Now, we just got done covering a lesson previously about log properties, and if you'll remember that lesson, we talked about any time you have an exponent on the inside of a logarithm, you can take that exponent and you can put it in the front of the log. So if I do that, we get x log 4 equals log 11. Okay, so I want you to look at that for a second. This is x times a number equals a number. So if I want to isolate the x, all I have to do is divide both sides by log 4. So if I do that, the left side, you just get x, and on the right side, you get log 11 divided by log 4. This is something you can type in the calculator. Now let's look at the connection between what we have written down now and what I did previously. Look at what I have here on my left finger, and look at what I have here on my right finger. What you should be noticing about them is they're the exact same thing. So regardless of what you do, whichever method, 1, 2, or 3, it doesn't matter. The answer comes out the exact same every single time. Now I will tell you, this method is very convenient if you have a calculator that lets you type in whatever log base you want. A lot of times, teachers will teach this method, and students will prefer this method because they don't have calculators that allow them to put in whatever they want. So why is it more beneficial, do they think, that I can just say log both sides? Well, this calculator has a log button in it. So if I have a calculator that just lets me do log or ln, why not just use log and ln all the time, which you can do. So let's move on to another one. In the next one, now we start throwing in this base e. Just because it's e doesn't make it harder. First thing, you have to isolate the power base. So the first thing you have to do in this problem is add 7 to both sides. You have to isolate the power base. So we get 4e to the negative 3/10 x equals 20. The power base is still not isolated. We have to divide by 4. And so what I will have is e to the negative 3/10, oops, wrote that wrong, equals 5. And here's where you want to get the power down. Now to get the power down, what you want to do is log both sides. Now here's the nice thing about this one. The logarithm form of e is natural log. So if I do the natural log of both sides, and I do the natural log of 5, the nice thing about this problem is my calculator has a natural log button. So use the button that we have. So if I do that, these two things cancel out because they're inverses, and you get negative 3/10 x equals the natural log of 5. Don't write this as a decimal yet because there's no reason to. The last thing we're going to do to solve for x is divide by -3/10. So on the left side, all you get is x. On the right side, you have this fraction to simplify. Well, the nice thing is, since my calculator has a natural log button on it, all I have to do is use that button. Now I'm going to switch calculators because this one's getting a glare on the screen and this one won't. Same operations though. I'm going to use the exact same buttons. So if I want to put this in, I'm going to do natural log of 5, so ln 5, close my parenthesis, and then divide by -3/10. And I will get a decimal, and I want 4 decimal places. So -5.364, and then that 7 will bump up to an 8. Last 2. Actually, there's going to be one more after these 2, so there's 3 left. Okay, so the next one looks really scary. Now let's talk about why it's not as scary as it looks. What I want you to see here is, what does this kind of look like? To me, it looks kind of like a quadratic. So if I rewrote this in a quadratic form, say I rewrote it as u squared minus 2u minus 3. Say I wrote it like that. Now I want you to look at the similarities between these. We've got something squared, -2 times something, -2 times something. A -3 and a -3. This, what I just did, it's a concept called U substitution. This is something that gets used a lot in calculus. And so all I did was rewrite this in a form that's a little easier to manage because all I'm going to do is factor this. So if I factor that, my factors should be u minus 3 and u plus 1. Now here's the deal. I don't care what u is. That's not what I'm trying to find. I'm trying to find x. Now I want you to look and see, what did we replace the u for? We took this u and we put it in place of this e and x. We took this u and put it in place of e of x. So what I'm going to do is go back now, and instead of using u's, I'm going to put e to the x in each one of these. So what I have is still like a zero product property kind of problem. All I'm going to do is take each of these, set them equal to 0, and solve. So the first one, if I set that equal to 0, I would add 3. So we get e to the x equals 3. If I take this one and set it equal to 0, we'd subtract 1. So I get e to the x equals -1. And I'm going to solve each one of them by using a logarithm. Now think about what logarithm cancels out e. That would be natural log. So I'm going to take the natural log of both sides. What cancels out e? The natural log does. So I'm going to take the natural log of both sides. Now here's the deal with this one. There's something we discussed in class the other day. If you try to take the natural log of a negative number, if you try to take any log of a negative number, your calculator is going to tell you error. That's because this does not exist, DNE. You could also write down that there's no solution. You could also write down that it's undefined. Any one of those answers would be fine for that problem. So the last thing then we have to do is we have to figure out, well, what's the answer for this one? Well, if I take the natural log of both sides, I have x equals natural log of 3. Well, luckily for me, I have a button in my calculator that lets me do that. So all I have to do is type it in the calculator. So we're going to take it and give 4 decimal places. Natural log 3, and there's your answer. Now if I write it correctly, 1.0986. There's your one solution. Next one. This one looks overly complicated, and it's not at all. And here's the reason why. We learned about exponent properties at the beginning of the school year. We talked about the fact that anytime I have two things that are the same base, if they're being multiplied, you can add the powers together. So all I'm going to do is put these two terms together as 5 to the 6x power. Don't multiply the 5's together and tell me that it's 25 to something. If you're multiplying same base, the base stays the same, the powers add together. Now this problem is just like the ones we started this video with, where if we can write them both as the same base, then I can solve the problem very easily. 125 is the same thing as 5 cubed. So I'm going to write it that way. 5 to the 6x equals 5 cubed. Since the bases are the same, I can set the powers equal. 6x equals 3. And if I divide, I get x equals 1/2. So a problem that looks scary doesn't end up being so bad. One more kind of problem we need to talk about, and it's the most complicated version. So let's talk about something like 7 to the 2x equals 5 to the 3x plus 2. Okay, so this looks very complicated, and the reason why it should look complicated to you is because these bases are not the same, so I cannot just set the powers equal. There are x's in both powers, which is a problem. So the first thing you want to do is get the x's out of the powers. And the easiest way to do that is to take the log of both sides. In this case, instead of doing log of both sides, I'm going to do natural log of both sides, because technically you can do either, since both of those buttons are in your calculator. Now, remember your properties of logarithms. That power now can come down on the front. So this is 2x ln 7. The other side, that power comes down on the front. That is 3x plus 2 ln of 5. So what are you going to do? First thing, this is a numerical value. If you really wanted to, you could change it to a rounded decimal right now. I'm not going to. This is a numerical value. I could change it to a rounded decimal right now if you wanted to. I'm not going to. All I'm going to do is distribute into the parentheses. 2x natural log of 7 equals 3x natural log of 5 plus 2 natural log of 5. So it gets messy before it gets better. The next thing you want to do, any terms that have x's in them, you want to put them on the same side of the equal sign. So I'm going to take this term and I'm going to put it on the left by subtracting. Resist the urge. You cannot combine these because the log portions here are different. So you have to write this as 2x minus, let me write this correctly. 2x natural log of 7 minus 3x natural log of 5 equals 2 natural log of 5. Unfortunately, there's nothing simpler you can do with it. So it's messy. What do you do with it then? Notice both of these terms have an x in them. My goal to solve this problem is to isolate x. So what we're going to do is factor an x out of both of these. So you're left with 2 ln of 7 minus 3 ln of 5 equals 2 ln of 5. If I want to get x by itself, all I'm going to do is divide by what's in this parenthesis. Remembering, this is just some decimal. I don't know what the decimal is right now. I could put it in the calculator and figure it out what it is, but the earlier in a problem you put stuff in a calculator, the more off your rounded answer is going to be. So all I'm going to do is divide both sides by that parenthesis. Left side, they cancel out. On the right side, this goes right into the calculator. So in my calculator, let's talk about how I would put it in. Anytime you want to put a fraction in, you have to do numerator in parentheses and then use the division symbol, denominator in parentheses. So that's exactly what I'm going to do. In the numerator, 2 ln 5 divided by, in the denominator, 2 ln 7 minus 3 ln 5. So notice that my numerator, the whole thing is in parentheses. Notice my denominator, I started a parenthesis, ended a parenthesis. And that is my value of x, 3.4372 if you round correctly. Of all the problems we've talked about in this video, this one's the most complicated one. On your worksheet for the homework for this, there are, I think, 2 examples like this. So work through them slowly. There's a lot going on, and make sure you ask questions if you have questions.